It probably goes without saying to everyone here that we want to know something about the lunar interior, but we have very few ways of making direct measurements of them and of it. And the best way is to look at glass beads that come from fire fountains. And the reason we want to look at the lunar interior is because some of the most important parameters about the lunar interior are oxygen fugacity and hydrogen fugacity. And so in our work, we've been looking at the valence state of different multivalent elements as a proxy for understanding oxygen fugacity in the lunar interior. And we're also interested in how oxygen fugacity relates to hydrogen fugacity. And it's very difficult to measure both of those things at nanoscales, but we've figured out ways to do that. So here are some examples of the sort of samples that we're studying. We've studied in the past some earlier Apollo samples, and we're fortunate now to have access both to the ANXA-1 team samples and the ANXA-2 team samples. So as you may not be aware, the ANXA cores are pretty cool. The ANXA-1 cores covered two different places, 73002 and 73001, and we were fortunate to find beads in several different intervals of both of these cores. And this is not a trivial exercise. These beads are tiny. They're a few microns across, and in order to study them, we have to find them, polish them, and then have a flat surface that we can analyze. So it may look like in this talk we haven't looked at very many samples, but we've looked at a bunch of samples and they're teeny tiny, and you actually don't know what you're looking at until you put them in the instrument. So it's been a very challenging study for me. And we've also been fortunate to have the support of the RISE consortium at Stony Brook, but most of the work that I'm going to present today came from the group of the SCARAB consortium, and these are some of our goals. Okay, so here's the model that we're working with, and I'll spend some time on this now that I've rushed through those introductory things. So a magma starts out in the lunar interior, and it has long been believed that the lunar interior was highly reducing, so very little oxygen. But as things begin to ascend in the lunar interior, it's believed that whatever volatiles were present at depth begin to exsolve, and as they do that, the environment becomes more oxidizing. Then you have yet another environment that happens when you erupt the samples, because now you've taken these glass or the melt droplets and you're surrounding them with this cloud of exsolved volatiles. And so there's very complicated possibilities that can happen in this cloud, which are illustrated in this cartoon here. So on the top row, we show what happens. So let's imagine that a hydrated lunar glass magma cools, and as it quenches, the hydrogen is desperately trying to get out, because there's in a lunar vacuum, hydrogen wants to escape from a hydrated droplet. On the other hand, some droplets may stay longer in the cloud, and that's what's shown on the bottom row here. So they start out hydrated, then many of them completely dehydrate, and then they may or may not oxidize. So very complicated processes going on here. And it's important that we understand them, because we want to be able to work backwards and authoritatively understand what's going on inside the moon. So we used FTIR to do the hydrogen measurements. Many people don't use FTIRs this way, but we were stuck because of the nature of the samples with the inability to make doubly polished samples. But even in reflectance, you can see, again, the color scheme here on the right-hand beads is high hydrogen is the light colors and purple is the low hydrogen. You can see that some of these beads actually are zoned. And, the top one is a perfect example of a bead where the melt is actually dehydrating. Here's another one, different bead, but you can see what the profile looks like. Again, quite compelling evidence that these changes are happening. And we had to look at like 10 beads to find one that was zoned like that. Many of them are either completely flat hydrated or completely flat dehydrated. But again, this gives you an idea, going back to our cartoon, that sometimes we see the opposite trends. So this is a different bead, 73001-461D, and now we have hydrogen going in. So as I said, lots of different permutations in these samples. And I think our hypothesis is that everything is related to where it was in this evolving cloud. So the numbers that we're getting, you can convert these reflectance to measurements. There are absorption coefficients for those, and you can actually get numbers that are quite comparable to what we get from the ion probe. So we're pretty sure we're on the right track here in terms of at least the semi-quantitative, I guess is what the word I would use, measurements of hydrogen concentrations in these beads. So now back to our little cartoon. Now I want you to switch gears and think about oxidation and reduction. And for this, we're of course using synchrotron X-ray absorption spectroscopy. This work was all done at the University of Chicago. And now we can make maps using different elements. We found that chrome was a really sensitive one. And here are some examples of what you see when you look at the same glass beads. Now we see that they have oxidized centers and reduced edges. How does that relate to hydrogen? I'll get to that in a second. Here's another one that's the opposite. Oxidized in the middle, reduced on the edge. And again, our hypothesis is that these things are tying back to processes that happen as the eruption is going on. Here's some other samples that have beautiful gradients. At the bottom on either side, you can see that there's a high in the middle and a low on the end when you plot oxidation state. And then this is a sample in which we have both FTIR and synchrotron data. And this one is really interesting because this particular bead is dehydrated on the edges and also reduced, which is an interesting combination. It's exactly the opposite of what we hypothesized. And it's also oxidized and hydrated in the middle. So, man, there's still a lot of science to be done here. It's really a meaty subject. Oops. There we go. And here's just a summary. So as you can see, there's sort of a variety of things. Some of them are all oxidized, some are flat, and some of them have oxidized cores and reduced rims. It's a sort of an interesting group. Oh, I guess that's my last slide, and I can't go backwards. So.
Oh, you can.
Oh, you can. Oh, it's the little button. So I'm going to stop there, and maybe there's room for one or two questions.
Yeah. Any questions in the audience, Darby?
So Q&A mic on the stand back here.
Oh.
Okay.
Don't everyone speak at
any
once.
questions online? Sorry, Sonia, I guess do we have any in chat?
I don't see any right now. If not, I could ask a question.
I don't hear any.
All right.
Wait, you're not free though. I have a question for you. I know
Yes.
you have to get a flight. Your point that is endogenous, all the geochemistry, which I really like just philosophically, but there are exogenous processes can happen like solar wind implantation, which can hydrogenate and maybe reduce. Do you see any evidence of that occurring, potentially explaining some of this?
Well, the problem is that most of the cases we see, it's concentric around the bead. And I would think that if there was some kind of exogenous process, it would disproportionately affect one side of the bead or the other. And we don't see that. But of course, these things are in a big pile. So, who knows?
Agreed. All right. Thank you so much.
Thank you.
Thank you.